Today I'm going to be talking about the ability for some minerals to fluoresce under the application of ultraviolet light. In this scenario I will specifically be using 365 nanometers with an approximate strength of 5.4 milliwatts per cubic centimeter, which is comparable to the strength of that same wavelength of light from the Sun at Earth's surface. Fluorescence occurs when electrons jump orbitals by the excitation of this shortwave light and in turn release energy. Always remember to use safety when working with ultraviolet light, as direct, prolonged exposure to the retina can induce cataracts. Here we have some quartz and biotite, and under the application of ultraviolet light they will emit different colors. And that is due to the trace impurities, or the metal cations within the mineral structure. This is a septarian nodule comprised of calcite, aragonite, and a bentonite clay. To the right of it is a sodalite, to the left is a gypsum. When you apply ultraviolet light to these, we get a much different color. These are sweetwater agates from Wyoming, and behind them a willemnite conglomerate from New Jersey. In the UV light spectrum, they exhibit much different color properties. This is a chalcedony, also from Wyoming, in the visible light spectrum, and in the ultraviolet light. These are hydrothermal breccias from New Mexico in the visible light spectrum. In the ultraviolet, minerals such as fluorite, lapis lazuli, calcite, kyanite, and opal will exhibit a strong fluorescence in ultraviolet light. What gives minerals their unique color with fluorescence is what's called activators, or trace impurities of metal cations in the mineral structure. Here is a septarian nodule from Utah and mineral concretions from the Morrison Formation in Wyoming, both comprised of calcite and aragonite. Approximately only 15% of minerals will have the ability to fluoresce under the application of ultraviolet light.